I'm intentionally talking about the things that I'm intentionally talking about the things that I think people are struggling the most with. So, just so you know, I'm talking about the hard stuff. I didn't come here to talk about the easy stuff. So, yes, the other way to do this problem, guys, the other way to do this problem is to remember that there is a connection between the kernel and the range, the sizes of the kernel and the range. Everybody absolutely needs to know this formula. The dimension of the kernel plus the dimension of the range adds up to how much? Do you remember? Right, the dimension of V. Very good. So if you know that formula, then usually the dimension of V is kind of a no-brainer. So you look here, you see it's obviously four-dimensional. So this one is 4. These two numbers have to add up to 4. So if you did your kernel correctly, the kernel here is 2-dimensional. So if this is a 2, then you already know that the dimension of the range is 2. And at the same time, not only is the dimension 2, so is the dimension of the whole W. All of W, the whole capital W is only 2-dimensional. You just concluded from there that the range is 2-dimensional, so the range must be the whole W, because they have the same exact size.
Would we be able to just do that?
Yeah, you could just do this. However, I like practicing. What if I had asked the question in the opposite order and it said, what's the range first?
And I would figure out other things first.
You could, if you really don't like the range. Actually, this is one way to sort of finagle your way around. Like you say, I really like the kernel, but I don't like thinking about the range. You can kind of avoid the range, or at least somewhat avoid it, by knowing this equation, because you can focus on getting the kernel right, and that will at least tell you the size of the range, which is a big step in sort of figuring out what it actually is. Okay? Guys, we're not going to resolve all of every issue that everybody in the room has with all the material like in this session right now. What you need to be doing is taking notes to yourself. If this is something that you don't remember, or you're not fresh on, or you need to go back and practice, well then this was a good thing that you're here right now to see this, to remind you, oh, I don't remember that very well. I better go do a few more examples of it. Yeah, Aaron?
Now back to the basis thing for the span
Yeah.
of the range of T.
Yeah.
Now, will we have, if you're asking for a basis,
Right.
will we plug it back into the transformation? Or
If I want a basis for the range, it's just these two things, without the span in front of it. Basis for range of T is a set of 1, 0 and negative 1, 2. But, guys, remember when I ask you for a basis for something, the answer is not unique. There can be lots of right answers. So if, for example, Fadi doesn't like that basis, we can certainly change it to 1, 0 and 0, 1. And that would be perfect. Sorry. And just go back to the point you made, which is that this basis isn't the only one. There might be a better basis in your mind. But there can be lots of right answers. But what do all bases have to have in common with each other? The dimension, the number of vectors in that basis. And of course, yeah, the definition. It's linearly independent and it's a spanning set. Okay. We all right with that? Kevin?
you just say 1, 0, 0, 1, 0?
Mm-hmm. Yeah, I mean, as soon as you know that R2 is what the range of T is, then when I'm asking you for a basis for the range of T, that means I'm really just asking you for a basis for R2. And you can come up with, I could probably, that'd be a good test question, give me 10 different bases for R2. All you got to do is make sure that you come up with 2 columns that give you an invertible 2x2 matrix, right? You remember that for Rn? Maybe I should refresh your memory about that real quick. It's not on the review sheet. But if I give you the right number of vectors, let's say I ask you for a basis for R7 and I give you 7 vectors. then do you remember that those vectors, either they are both linearly independent and a spanning set, or they are neither? It's the right number of vectors, so when you put those vectors in the columns of a matrix, what size will the matrix be? It'll be a square matrix. The K and the N, or the rows of columns, will be the same number of each. And anytime you have a square matrix, one of the themes we've learned this semester is we can usually take the determinant of it, see if it's invertible or not. Invertible is sort of a good thing, right? So if your matrix is invertible, then it must have been both. It was linearly independent and a spanning set. If you know that, and let's say you calculate the determinant and you get it wrong, at least you're using the right method, and I'll be able to give you the partial credit for knowing that by taking the determinant of this matrix whose columns are your proposed bases, you're going to get an answer as to whether it really is a basis. Knowing that that's valuable Math 250B knowledge to me. So I'd like you to get the determinant right too, but that comes under the heading of you can get lots of partial credit for knowing the right process to go through. So, okay. So I don't remember who asked that question, but I hope Kevin, I think. Did I answer your question? Okay, super. Anybody else? Have I prompted any other questions along the line here so far? Okay. Maybe we should talk about inner product spaces for a little bit.
Yes.
Okay, let's do that. Let's do that next. I've got a number of examples of that. Let's see. Actually, before we go into any more of the problems, let's just try and remember the axioms. So, axioms for inner products. By the way, this is all 4.11 and 4.12. So, remember, an inner product space is really just a vector space with some extra geometrical structure thrown into it. Okay. So, how many axioms were there? 4. Okay. Does anybody remember the first one? Right. The inner product of x with itself has to be at least 0. And when can it be 0? Right. Equals 0 only if x was the 0 vector. So that's actually often the axiom that can sometimes go wrong for a proposed inner product. Okay, does anybody remember another inner product axiom? Let's hear it from somebody else. Okay. Bobby?
XY equals YX.
Inner product of x and y equals the inner product of y with x. Sounds good. Somebody else want to give me the third one?
xk comma y is equal to.
I'm going to always put my constants in front. Kx and what was the second one? Y, okay.
Is equal to x, ky.
No, it.
No.
K comes out and then you can put it back in.
Yeah, but the axiom is just, the k comes right out. I have to combine with the second axiom to put the k in the second slot. So I just want to get the actual axiom. So there, the k just factors right out. Okay, and does anybody remember the last axiom? We really have not had to work with it too much. It's usually true. It's the one where if you have two vectors, say x1 and x2, and you add them, and then take the inner product of the result with y, then, right, inner product of x1 with y, plus the inner product of x2 with y. Actually, I'm going to just make a little remark here. If we define a transformation, T, to go from V to R, via T of X equals the inner product of X with Y, for a fixed y in V. So if we fix a vector y in the vector space V, and we create a transformation that inputs another vector from the vector space and outputs the scalar, which is just this inner product value, then axioms 3 and 4 together actually prove that that T is linear. It respects from axiom 3 respects scalars. So T of kx would be inner product of kx with y. You can pull the k out, according to this axiom. And then the fourth axiom says that, well, T of x1 plus x2 will be T of x1 plus T of x2. You see that? So, is a linear transformation. Just to tie it into what we were talking about a minute ago. These things so often they tie together pretty well. Okay, so those are my axioms. With that in mind, let's try a couple of problems off of the review sheet here, okay? So let's look at number 6 first of all. Number 6 says, let's take V to be P2 of R. And I'm going to give you a proposed inner product. Namely, I'm going to take A naught plus A1x plus A2x squared, inner product that with B naught plus B1x plus B2x squared. And I'm going to define that to be equal to A naught B2 plus A1 B1 plus A2 B naught. I'm going to just create that formula. And what I'd like us to try to do is to try to show that that is actually not a valid inner product. Show this is not a valid inner product. Okay? We'll try and show that this will fail to be a valid inner product. Which basically means there has to be an axiom that doesn't work. And we have to illustrate it with an example. So I need an example to show that one, I only need one of my axioms does not hold. Does everybody understand the question so far? Let's just make sure. These are quadratic polynomials. I take the inner product of two polynomials and I get what kind of an answer? A scalar, right? Remember, the inner product always spits out a scalar. So you're getting a scalar result here, right? But then the question is, are these axioms satisfied? Do we have something that makes sense? So, anybody have any ideas? Jake?
I think if you make A0 and A2, I'm sorry, A0 like like 1, then A1 negative 1, and A2 1.
So that would be choosing a specific element, a specific polynomial. So A naught is 1, A1 is negative 1.
Take A1 negative 2,
Oh, you want negative 2
Yeah.
there?
and then make everything else just 1. Like on the B side, would be 1, B0, 1, 2.
So wait, what do you want over here?
1 plus x squared.
Okay. So that's what you want?
Yeah.
Alright, let's work it out. A naught times B2 would be 1 times 1, which is 1. A1 times B1 would be negative 2 times 1, that would be negative 2. And then I'm using this formula, A2 times B naught, that would be 1 times 1, right? Which is 1, that adds up to what? 0. Anything wrong with that?
Nope.
Absolutely nothing wrong with that. All that shows that these two vectors are perpendicular, okay, in the context of an inner product. That's actually worth refreshing our memory. When you take the inner product of two vectors and get 0, it means they're perpendicular. Nobody remembering orthogonal sets, right? The reason, I know what you were trying to do, the problem is that what you need to, getting 0 here would be great if it was referring in reference to the first axiom. But if you wanna use the first axiom, you have to use the same polynomial twice, right? So Brandon, do you
So
want?
would you make a matrix that is 0, 1, 0, 0, and then 0, 1, 0, 0?
I don't want to use matrices. These are polynomials.
X squared minus 1. Yeah.
Do you want me to start over?
Yeah.
I guess so.
Just,
Go ahead.
just x squared minus 1 and the itself.
Okay, let's try that. Now at least we have the same thing in both slots. Okay, so A naught, which is -1, times B2, which is 1, that's -1, right? And then the x term, the A1 times B1, that's just the x coefficient times the x coefficient. There's nothing in the x position there, so that's not there. And then the A2 times B naught, well, that would be 1 times -1, so we are getting a negative number, right? Now we have a good example to work with, because we took a polynomial, we inner product with itself, and we got a negative answer. It violates axiom 1. So that's what we would just say here, less than 0, so axiom 1 fails. And so we're done. Now there's 1,000 other examples you could have given. But it really does need to be, at least for this example, does need to be that first axiom is the one you want to focus on. Okay? Yeah, Priscilla?
Was there any way to like prove it without like giving like a specific example, just using like the x and x? Not really.
Not really. I mean, you would have to sort of say, well, this is, if you use the same polynomial twice, then you wouldn't really have B naught, B1, and B2. You'd have A naught, A1, and A2 twice. So here you'd have A naught times A2 plus A1 squared plus A2 times A naught, and you'd have to just try and choose values of A naught, A1, and A2 that make it negative. Yeah, so it's probably just as simple to kind of come up with a specific example. Okay. You know, again, if you'll find examples of this, other illustrations of things that don't work in the review packet, you should definitely take a look at some of them. Now, on the other hand, number 7 on the review sheet is slightly different, and it turns out that it does work. So, B is equal to P2 of R, again. And this time, they're going to take the inner product of A naught plus A1x plus A2x squared together with B naught plus B1x plus B2x squared. And this time it's going to be defined to be A naught B naught plus A1 B1 plus A2 B2. So this time the entries are lining up. Same subscripts. Okay? See the difference? Yeah. See, here the subscripts were mixed. And here we're using the same one. Okay? So this time it says show that it is a valid inner product. Which means you got to show these axioms. All 4 technically, if it says that. Am I still good?
Yeah, you're still good.
Okay. All 4 if it says that, but then of course I might just ask you, I could just ask you to show 2 out of 4, or pick your favorite 2 or something like that. You know, so I could do that. So let's see if we can do some of this. Maybe I won't do the whole thing. Show that this thing is a valid inner product. I always like to check the first axiom because that's always the one that seems to be problematic. So if we look at, so axiom 1, A naught plus A1x plus A2x squared, inner product with itself, right? Well, we just use this formula, so all of the b's are really just the same as the a's. So this is just A naught squared plus A1 a1 squared plus a2 squared, right? And that's just a bunch of numbers that are gonna be at least 0. So you're adding them together, it's gonna be at least 0. This is actually just kind of like a normal dot product, which we know is a good example of a new product. So there you go, it's at least 0, and it's only equal to 0 if a naught equals a1 equals a2 equals 0. In other words, if you started with the 0 polynomial. Okay.
Do we need to write that down?
This last part, you should. You should put that. You should add that onto the end of it. It is part of that axiom.
I just forgot.
Make sense? Anybody want to see any more of these parts?
How many do you have to show?
Well, technically all 4. It says show it's an inner product, so you technically have to show all 4. I don't want to drag you down the road of doing that right now if you don't want to see all 4. It's unlikely that I would actually ask you on the final to show all 4 axioms of something. I would more likely give you a choice to check some of them, but it's up to you guys. You think you need to see this? Let's not do it. I think it's, what did I say in the solution?
I think you only did 2.
Did I?
Yeah.
I wondered if I got lazy. Oh no, I did all 4.
Oh, really?
Oh yeah. I went full blast. I did everything. I did it. I totally worked out. Okay. There you go. There you go. However, I would like to do one other thing here with this. Let's find.
You should give us all the evidence.
These axioms are very natural, right? They're not. It's not like they're mysterious or weird. They're kind of natural mathematical properties. So I do want to do one thing with this, which is, so this is part B, I guess, of this whole problem. 7b is find the angle between p of x, which is going to be 1 minus 2x plus 2x squared, and q of x, which is going to equal 2 minus x squared. That's probably worth checking. Okay, so anybody know what formula is being used here? Or what formula is relevant here?
Second one?
It's not an axiom. Actually, no, we're not talking about it. We're talking about the angle theta. There's an angle theta between these 2 vectors. If anything, you might remember the formula from 250A. If you take the dot product of 2 vectors, which in our context will become inner products, so let me write it as an inner product, right? The formula is, and everybody should know this because you took 250A, it's you did, the norm of V times the norm of W times the cosine of the angle between the 2 vectors. I'm simply asking you to find theta. And of course your final answer is going to be in the form of arc cosine of something because you don't have a calculator to work it out. So you just leave your answer as arc cosine of something. But anyway, what is the inner product of P of x and Q of x? Because those are the 2 vectors that we're looking at here.
2.
It's 2 plus 2 minus 2, right? Okay guys, I'm using this formula again. I multiply the constant terms together, I multiply the x terms together, and then I multiply the x squared terms together. So the constant terms, 1 times 2 is 2. The x terms, that would be, well, negative 1 times negative 2, that's also 2. And then the x squared term is negative 1 times 2, that's negative 2. So the whole thing comes out to 2. What is the norm of oh, we didn't go over this yet, but I think everybody remembers the norm is the square root of,
The inner product.
right, the norm is the square root of the inner product of the vector with itself.
Over this shape.
So what's the norm of p of x gonna be?
No, 8, 9, 9.
Square root of
3
1 plus,
plus 4 plus 4.
1 plus 4 plus 4, right?
9 to
9, square root of 9 is 3. Great, okay, so we get 3. How about the norm of the vector q? Radical 6?
Yeah.
That's what I'm getting. Okay? Kind of doing these in our head quickly. Right, so 2 times 2 plus 1 times 1 plus 1 times 1, that adds up to 6. The square root of 6 is therefore the norm. And this is times the cosine of theta. So your answer now would just be theta is the arc cosine of 2 over 3 radical 6, and you obviously would not be expected to simplify that. You just leave it in that format. That makes some sense? Okay, I got one more part to this question. Yeah.
Is, like, the inner product in the view always going to be like A0 or,
I could give you something, I could come up with something weird.
oh, but that part's always skipped.
Yeah, it has to be given.
Okay.
Yeah. What? Oh, actually, good point. I need to slow down a little bit about when I make that statement. If I give you a question about inner product spaces and you don't see an inner product there, right, then you have to assume that you're using a regular dot product, right? That would be for Rn only. So if I give you a problem in Rn and I say find me an orthogonal basis for some subspace of Rn, you would know that even if I didn't tell you what the inner product formula was, that you would be using the regular dot product. On any other example, if it's polynomials or matrices or some other weird vector space that I am equipping with an inner product, I would have to tell you the formula for it. So I'd have to give you this formula. Or I could do something bizarre. I could give you Rn, but I could change to not the standard inner product. In other words, I could take away the regular dot product and say I don't want to use that. I'm going to give you a different one to use, and I'm pretty sure there was something in 4.12 when we did some problems like that. There too?
If you give us an alternative
Yeah.
product and you want us to find the angle between them, are we supposed to use that?
The alternative one. Yeah, if I give you an I'm not going to give you any problem where there's 2 inner products to be juggling in your mind at once. There'll only be 1 inner product at a time, but it might not be the standard one. The reason why I might go away from the standard one is just to really make sure you know the concepts, and they're not just relying on knowing how dot products work, right? So so make sure that's why it's good to do some of these examples that involve polynomials and other kinds of objects. So you're not just feeling like you're doing a glorified 250A problem. You're actually doing something where we're taking a more unfamiliar vector space, something that we learned this semester, and equipping it with an inner product. So let's follow up here on one last thing here on this problem, and then I'm going to be feeling pretty good about this. Find an orthogonal basis for S, which is going to be the span of 1 minus 2x plus 2x squared, comma, 2 minus x squared. And we're still using the inner product that we have over here on the far right. Okay, so, yeah, Fadi?
Is this where you set B1 to be the first one and B2 and then
What's that process called?
Gratification?
Yes.
Which you're gonna give us?
I'll give you the formulas for those. Yeah, so you're not gonna have to worry about that part. First thing is, I want everybody to realize these 2 polynomials are not scalar multiples of each other, and there's only 2 of them. So they are a basis